Hey, how are you doing? As we continue through Unit 9, we are looking at parametric and polar equations and then vectors. Vectors are just another take on that parametric equation. If you have physics at the same time right now, you'll see some similarities, and what you do with vectors in physics is a little bit more in depth than what we do here in calculus. So I like to think of vectors in calculus as just another way to look at parametric equations. So students will be able to graph vectors, perform basic vector computations, and find a unit vector. A vector is used to represent quantities that have direction and magnitude and length. A two-dimensional vector is determined by 2 points in the plane. A couple things to know. We can have our initial point. My pencil's not synced up. One moment, please. All right, a vector is determined by 2 points in the plane. So we have the initial point, our initial point P, and then that's the tail or the base point. And we have the terminal point, usually called Q. And we could write this as V is equal to the vector PQ. And then this is our notation, vector PQ. The length or magnitude of the vector is denoted by this double set of lines V, and it's defined as the distance from P to Q. And distance is always an absolute value, so that's what's going on over here. So for example 1, find the length of vector PQ. So we have the point P over here. You need the ordered pair, which is 2, 2. And the point Q is over here. The ordered pair, I don't love this graph, but it's 7, 5. So the length of PQ is our distance formula. Remember, it's x2 minus x1 squared plus y2 minus y1 squared. So we're going to say that it is 7 minus 2 squared plus 5 minus 2 squared. So I've got 5 squared plus 3 squared, which is 25 plus 9, which is the square root of 34. And 34 is 7 times 2. That doesn't break down any further. So we have the length of the vector, the square root of 34. Two vectors of non-zero length are parallel if the lines running through them are parallel. A vector undergoes a translation when it's moved parallel to itself without changing in length or direction. Two vectors with the same length and direction are equivalent, and every vector can be translated so its tail is at the origin. This creates a vector in standard position. So for example, if I could take this vector PQ that's up here up above, pick it up and move it down here to the origin, you can translate it and move it. It has to have the same direction. It has to have the same magnitude, but you can change where it starts. So vector PQ, again, that point P, the beginning point, has the coordinates AB, and the terminal point has the points AB, but the second version of those. That A would be A2 minus A1, and the B is B2 minus B1. So that's to get your component form of your vector. We assume that all vectors are based at the origin unless otherwise stated. So if they don't tell you, just assume that it's at the vector. And the zero vector is 0, 0. 0 in the x direction, 0 in the y direction. So for example 2, I want to find the components of vector 1, which is P1, Q1, and vector 2, which is P2, Q2. So we are given this information. What we want to know, talk about vector 1 here. Well, let's talk about, we have our points. Vector 1 is focusing on P1 and Q1. So the components of vector 1 would be 6 minus 3 and 5 minus 7. Oops. Got a lot going on here. So vector 1 is really 3, negative 2. Those are the components of vector 1. And if we look at vector 2, it would be 2 minus a negative 4 and 1 minus 4, which would be 6, comma, negative 3. All right, so if we look at these, what's really going on here? If I look at my coordinate plane and we have the vector or the points 3, 7, and 6, 5, let's start there. 3, 7 is right 3 and up 7, 2, 3, 4, 5, 6, 7. There's P1 and Q1 is at 6, 1, 2, 3, 4, 5, 6, and up 5, 1, 2, 3, 4, 5. And here's Q1. So here's that first vector. And the second one is at the point negative 4, 4, 1, 2, 3, 4, 1, 2, 3, 4. So there's P2 and Q2 is right 2 up 1. Here's Q2. So what we're saying by that component vector is we're basically just, it's almost like slope, that this one and over here is vector 1. It's going right 3 and down 2. And then vector 2 over here is going right 6 and down 3. So kind of the same idea as slope. So it's like you're imagining the origin right here at the starting point for each one of those. That's what you're really imagining. Example 3, sketch the vector 2, negative 3 based at 1, 4 and the vector equivalent to V based at the origin. So kind of working backwards to what we just did a moment ago. Draw yourself a coordinate plane. If I'm based at the point 1, 4, 1, 2, 3, 4, there's the point 1, 4. My vector 2, negative 3, let's make this one green. So it's kind of going right 2 and then down 3, 1, 2, 3. There would be my terminal point. Draw the vector. So there's vector V. And then draw the vector equivalent to V based at the origin. So do it again, based at the origin. So you'd go right 2 and then down 3, which would be somewhere here. Those are the two versions of the vector. There you go. Vector algebra, your scalar, and this is this Greek symbol. I think it's a lambda. I'd have to look that one up. Scalar, and then V is your non-zero vector. You don't want it to be 0, 0 because anything times 0 is 0, so that doesn't work. V plus W, two vectors being added, is defined when they have the same base point. You can translate W so it coincides with the head of V. I think you've seen this before if you're a physics student. I think you've seen this in physics. But if you have something like V and W, you can translate W so it coincides with the head of V. So you can actually take this piece, oops, that's not going to do it for me, and move it so that it's up here. Translate the W up to here. So now you have another way of adding them. And then your parallelogram law, I remember this from physics a long time ago. Basically, you complete the parallelogram, and then when you connect the diagonal across there, when you add V plus W, this is your resulting vector. So this dark red one is vector V plus vector W. That's what you're left with. So something to think about there. To add or subtract vectors, we add or subtract the components. So vector V has the components A, B, and vector W has the components C, D. I have a few rules for you. V plus W would be equal to A plus C and B plus D. Same thing if you subtract them. V minus W would be A minus C and B minus D. And then if you multiply by that scalar W, this would be scalar A or lambda A and lambda B. Good. Example 4, if vector V has the components 1, 4, and vector W has the components 3, 2, find V plus W and then find 5v. So v plus w would be equal to 1 plus 3, and then 4 plus 2. So you get the addition here of 4, 6. Then if we want to do part B, that scalar, 5v, this would be 5 times 1, and then 5 times 4. So your components are 520. Good. A linear combination, if we want to express vector u, which has the components 4, 4, as a linear combination of 6, 2, vector v, which is 6, 2, and vector w, which is 2, 4. I haven't actually seen this too much, but you know, it's worth a try here. So we've got a bit of things going on. We have r, some scalar, times v, plus s times w is going to be equal to 4, 4. So some fraction of v and some fraction of w, when we put them together, we want to get 4, 4. So this becomes r times 6, 2, and s times 2, 4 has to be equal to 4, 4. So what we do is we kind of turn this into a systems of equations. Start with all of your x pieces first. This is kind of wacky, I know. So the 6 and the 2 and the 4. So you would say that 6r plus 2s is equal to 4. And then you're going to go through with your y components and do the same thing. This time we say, here's the 2, here's the 4, here's the 4. We would say 2r plus 4s is equal to 4. And then you have to go through and solve them. So do you remember Algebra 1, systems of equations? That's what we're looking at here. And in fact, I'm going to multiply this top one by a -2. So this becomes negative 12r minus 4s equals -8. In the bottom, we have 2r plus 4s is equal to 4. When we add these things together, negative 10r, those cancel out, is equal to -4. Divide by -10, divide by -10, r is equal to 2/5. Excellent. So we want to do it all again. Find the s. In fact, I'm just going to substitute that back in. They're both going to give me fractions, but that's okay. So 2 times 2/5 plus 4s is equal to 4. So this would be 4/5 plus 4s is equal to 4. I'm going to multiply everything by 5 to clear those fractions. So 4 plus 20s is equal to 20. 20s equals 16. So s is 16 over 20, which is 4/5. So r is 2/5 and s is 4/5. There you go. That's what the linear combination would be. Keep going here. A unit vector. A vector of length 1 is called the unit vector. It can be used to specify direction when length is not necessary. The head of vector E based at the origin lies on the unit circle and has the components E equals cosine theta for the x component and y has that sine theta component. Remember I mentioned that the other day? Where x would be your cosine and y would be your sine. Yeah, how about that? If vector v, AB, is a non-zero vector, then EV, this is my unit vector notation, is that vector divided by the length of the vector. So find the unit vector in the direction of v, which has the components 3, 5. So what we're going to do here is find the length of v. It's that distance formula. You could even say 5 minus, let's do 3 minus 0 if it's at the origin. 3 minus 0 squared plus 5 minus 0 squared. So 3 squared is 9, 5 squared is 25. This gives me a 34. the square root of 34. Now, to make it a unit vector, you take this 3, 5, and you divide it by the square root of 34. So let me change my notation up here a little bit. So 3 over root 34, 5 over root 34. There we go. There's your unit vector. So it has the same direction, but it has a length of 1. And finally, we have special notation for unit vectors in the direction of the positive and x and y axes. I is your vector that goes to the right, and j is your vector that goes right up and down. And I remember this from physics. We don't see it in calculus all that often, but instead of writing like the one above, we'll just use 3, 5. If I recall, we wrote this as 3i and 5j, showing direction. And one more thing just to know in the back of your head, your triangle inequality for any two vectors, v and w, the sum of the vectors together is less than or equal to the sum of the individual vectors. All right, I think you'll find that if you go through and think of these vector problems as parametric equation problems when you look at them, you will be much, much happier. They're not so scary. So you have your x component, your y component, parametric equations.